Good morning, everyone. We got a lot on our plate today. First thing is we're going to do some more of those integration test questions. To save time, you're going to do as I say and not as I do. So we would normally check that it is positive and find its derivative and show that the derivative was negative, and that meant that it was decreasing. So normally step one would be prove that the series is made up of positive terms, and step two would be prove that it's decreasing. I'm just going to skip by them, but you're not allowed to, right? You should be doing them all the time. That way we could maybe cut down on the time it takes when we do these questions and focus on what's probably going to be the hardest of them, and that is the integration part. So this is the guy I'm going to do for our first one. That one, which is similar to question 11. You can prove that this decreases, and you can also prove that it's positive, but we'll assume that's done. So now we're going to essentially find, and I made my first mistake, which I just got, starts at 2 to infinity. Does anybody know why this particular series starts at n equals 2 and not as the typical n equals 1 that most of them start with?
If it was 1, you would be dividing by 0.
Pretty much it. If they wanted to, couldn't they just start at 20 because they felt like it and it wouldn't really change anything? Right. So the start number has to be here for completeness, but normally your conclusion to is it convergent or is it divergent is that doesn't affect it, right? If you start at 20, it'll still converge. If it diverges, it will still diverge. So this is the guy that we're going to have to find the limit of. And by the way, don't do this. This particular question only has 2 answers that you choose from. Now, since you get 5 choices, couldn't you just pick the top one? And if it didn't work, you'd pick the bottom one, and that would take about 20 seconds and you would have done the homework. Don't do that. You need practice at doing integration, because when you do the test, right, the weekly test, you have a 50-50 chance of guessing it right. I mean, that's not a good average. Secondly, when you do the midterm, I want to see the working. I won't care what you put. I'll be looking at the whole, prove that it's positive, prove that it's decreasing, and now get that integral. And the midterm and the final are worth a lot more points than that quiz is, right? So just don't get into that bad habit. So this is going to be the limit as t tends to infinity from 2 to t of this guy. These integrals fall into 3 categories. Some of them, the easiest ones, are just a power, right? Add 1 to the power, divide by the new power. They're the best ones, they're the quickest. Some of them are u-subs, and some of them are integration by parts, and they definitely take a lot more time. What method will you use to integrate that fraction?
U-sub.
Correct. Now you have to decide what is the u-sub.
U equals natural log of n.
Or in this case x, but that's fine. I know what you meant. Are you happy with that u-sub? Well, you're thinking, where did that come from? When you see logs, don't logs kind of bend the rules? Normally, if you see a fraction, it would be the guy in the bottom, right? Or at least something to do with the guy in the bottom. In this case, it's only that one piece. And that's quite typical when there's a log involved. So I'll differentiate with respect to x. I'll do the crossover. And I'll then isolate the du. So it's now going to be the limit as t tends to infinity of the integral. Don't put the limits integration in, it's a bad idea. 5 x u times. What am I doing here? Nobody caught me out. Haven't I already isolated the dx? So I can just replace the dx with x du. It's just the way the cross multiplied happened, did it? I got distracted. So we have the limit as t tends to infinity of cancel 5 over u du. And that becomes the limit as t tends to infinity of 5 times the log of u. And that becomes t tends to infinity, 5 times the log. And u is a log, so it's a weird one. It's a log of a log. Evaluated at x equals 2 and then at x equals t. So at that point, we bring in the limits of integration again. So it's now going to be the limit as t tends to infinity of 5 times the natural log of the natural log of t. Take away 5 times the natural log of the natural log of 2. This one you can do a brute force on. It's going to be 5 times the natural log of the natural log of infinity. Take away basically just a number. Okay. The natural log of infinity is infinity. So if I wanted to write this line, but I probably wouldn't normally, it would be that guy, right? But isn't the natural log of infinity still infinity? So you get 5 times infinity, take away number. So you get infinity, take away number. So what you're looking at is diversion. And I put in a lot more lines. Was that a question?
Yeah.
Yes.
So when you did your u substitution, you did
Yes.
du over dx equals like 1 over x and then
Yes.
x du. So I'm just confused as to why that wouldn't, like the du wouldn't just be 1 over x dx for that, because if
It
you
would
do the
be.
derivative.
It would be, but what we want is an isolated dx. We want to find out what that dx turns into in terms of du. So in this case, I only needed to stop there. Now,
Well,
right, okay.
I'm sorry, my thought process for that would be if it was 1 over x for that, then you can substitute out that x in the underneath the fraction, and then it would just be 5 over, oh, okay, so that's my bad. Okay, I was
That's not
getting
bad.
caught up.
No, I tend to do these in the same way every time, but I understand what you're doing. But normally what I want to do is isolate the dx, because then I just replace that guy with whatever it is, and then everything cancels out. And what you said would have worked. It's just not the way I look at them. But it was totally correct. You didn't do it wrong.
I got caught up thinking I was doing it wrong, but thank you.
Okay. Right, so let's, well, that one is divergent, isn't it? Because the integral was divergent. And so you would put a dot there, but you would put it there because you actually did check for it, right, and test for it. And that's better than just, I'll guess and move on and do another one. So far, so good. Now, I won't do this one all the way to the end, but this one is a version of question 12. And it looks a little bit like the one we just did. And you can check that that is positive and that it's decreasing, because it is. And when you find the integral from 2 to infinity, you're going to be left with this guy. What method will I use to solve that integral. It's either a U sub or it's an integration by parts, and be very careful.
Would it be in integration by parts?
Yes. Doesn't it look very like a U sub? In fact, if the question had been this guy, it would have been a U sub. And who would the U sub be in this question?
U equals X.
Nope,
ln x.
ln of x. So if it was this one, a U sub of ln of x. But this guy, no. This guy, you are going to write him like that. And then you're going to rewrite them as a 2. Like that. Now, can you see two things multiplied, which tends to be, not always, but tends to be integration by parts. So now you have one more decision to make. Who is the F and who is the G? Integration by parts. Which one is f of x? Which one is g of x?
The natural log would be f of x, and then the x to the -2 would be g of x.
Can you remember back in Calc 2 doing logs and integration by parts? And wasn't the case almost exclusively that the f of x was the log thing? Remember? And that's what's happening here. So can you see that one is going to be a bit of a different method for finding its integral. And then it actually ends up being a U sub, a brute force at the end. And I believe it converges, but you can check it at the end. Now, we have probably, what's my brain saying? We have probably done enough examples of the integration test, because most of it involves you just learning how to integrate to infinity, right? So it's Calc 2 work, but it's very slow. But wouldn't it be nice if we could avoid doing the integral test, at least for some questions? You won't be able to avoid it for pretty much half the ones we've done. None of the ones we've done today, but about half the ones we did yesterday, you could avoid doing the integral test. And that's because there's another test, another test, called the P-series test. And the P-series test works for series that look like this. Oops, I don't know where that came from. 1 over n to the p. So for instance, if I had a series 1 over n squared, that would be a P series. And we would say it was a P series, P equals 2. You don't really need 1, you could start at 2. And if you had a guy, and it doesn't need to have a 1 in the top, it can have a number like 10, and you can have 10 cubed. And that would be a P series, P equals 3. You could have one like this. Over the square root of n. Now, if you got one that looked like that, it is a P series. What fraction would the P value be for this one?
1/2.
Right. So you might have to think of some of them like that, right? So how does the P series test work? If your series belongs to the family of P series, here's some examples of guys in that family, right? So if it looks something like that, right? Here is your test. If P is greater than 1, the series converges. And if P is less than or equal to 1, the series diverges. Isn't that a nice little test? So, would that one converge or not? 1 over n squared, would it converge or would it diverge?
Converge.
Because it's P, which is 2, is bigger than 1. Would 10 over n cubed converge or diverge?
Converge.
Because its P value is 3 and that's greater than 1. Would 2 over the square root of n converge or diverge?
Diverge.
Diverge. Isn't its P value a half and that is less than or equal to 1? Can you remember this guy? I keep bringing him back. Remember the harmonic series, 1 plus a half plus a quarter plus a third? Remember that guy? It's called the harmonic series. Isn't he a P series? Isn't his P value 1? Does this guy converge or diverge?
Diverge.
That's it. Now, would you agree, compared to the work you would need to do to prove these guys using the integral test, isn't this P series test a walk in the park? You just look at it. And so how would you officially do it in an exam? Not a lot. This is what I would expect to see. If you had a series that looked like this, just for argument's sake, you would just write down it's a P series. P equals 2. You would say the P value is greater than 1. So it converges. Would you agree that's not a lot to write down for the answer? What are you doing? You're telling me you recognize it's a P series. You're telling me you know what the number for the P series is. And you're telling me that the reason you made it converge was because it was bigger than 1. Do you see that's enough to tell me you know everything that you need to prove that that's convergent? Now, they might be sneaky. They might write it like that. What would that guy? It is a P series. What's the P value for that guy?
2.
Agreed. It's not negative 2. Agreed, it's 2. Because isn't that just another way of writing that guy? So they might try and catch you that way. Here's another way they might catch you, or try and catch you. What would n root n be written as if you write it as a single power of n? Because you need the bottom to be where the n's are, and you need a power to go with that n. What would n root n?
N to the 3 halves.
Would that converge or diverge?
Diverge.
It would converge.
Isn't it bigger than 1? Let's do that. You say it's P series. P is 3 halves, agreed. Isn't P greater than 1, so it converges? Remember the P series says if the P value is bigger than 1, it converges. If the P value is less than or equal to 1, then your conclusion will be that it diverges.
Why is it that when, like, let's say 2 divided by the square root of n, and you take it to infinity?
Yeah, well, if you take all of the P series to infinity, the terms become 0. But just because the individual terms become 0 doesn't mean that the series is finite, that it converges.
Oh, okay.
Right. Pretty much every series that you're likely to deal with, the individual terms tend to 0. And that tells you nothing about convergence or divergence. The few times that it doesn't happen, isn't that what the divergence test is there for? Oh, the individual terms don't become 0. They tend to a half. Oh, that's why it diverges then, right? because an infinite number of a halves would be infinite, right? And the divergence test is nice when you can use it, but you can't use it much because it doesn't happen that often. Are we good? P-series test. Let me find something. It's always hard to find things when you're not expecting to find them. Okay. Oh, great. Version of 16. This is not the P-series test, but I can use it to prove convergence. Would you agree that that is a P-series? Hopefully you would say that the P is 5. And isn't that greater than 1, so it converges? So if the question was, prove to me that that converges, haven't we got a ready-made test for it? Let's see if I can find one where they only ask you for convergence and nothing else. That would be nice. Not that one, not that one. Definitely not that one. Oh, here we go. This one might catch you out. I don't know. It's hard to tell. That's a weird looking one. It is a P-series, right? What number is P?
Root 5.
Yeah. Is square root of 5 bigger than 1? So doesn't this one converge? Just a weird number, right? How about this fella? Which is basically the one straight after it. It might not look like a P-series because of the way it's written. But that doesn't mean that it's not a P-series test. Hey, cut that out. You should know better, young lady. Okay. Do you see the way I've written it? It now looks like a P-series, doesn't it? Won't its P value be 0.9999? Converge or diverge?
Diverge.
Yeah. What about this one? Well, that's going to be a bit tricky. Because we don't have a formula. So we are going to have to figure out what that formula is. 1 gets you 1, 2 gets you that guy, 3 gets you that guy, 4 gets you that guy, 5 gets you that guy. So what does n get you? Well, I would think of that as 1 over 1. So it's 1 on the top. What do you do to 2 to get 8, 3 to get 27, 4 to get 64, and 5 to get 125? You do the same thing every time.
N cubed.
You do. 2 cubed, 3 cubed, 4 cubed, 5 cubed, right? There's no short way of doing that, isn't it? Just you look at it and you look for patterns. Now that I've written it that way, can you see it's a P-series and it converges? What about this one then? Same problem. 1 gets you that, 2 gets you that, 3 gets you that, 4 gets you that. What does n get you?
1 over n square root of n.
which I am now going to call into the 3/2. Great. So when you stick that into that format, can you see a P series now? And you're good to go. You like P series when you can see them? Right. If you couldn't see them, couldn't you do pretty much every single one of them using the integral test? It would just take a lot longer. We've got a couple of things still left. Forget about P series now. We're back to integral test and unusual situations. So first thing I'm going to tell you about is to remind you some integrals from a way back. Do you recognize the integral of 1 over x squared plus 1?
Isn't that inverse tangent?
It is. Forget about, technically I'll put the plus in, but that's going to disappear there. Okay, now, there was an expanded version. So you can actually find the integral of 1 over x squared plus any number, plus 4, plus 9, plus 25. They typically tend to be square numbers. Does anybody know what the integral of that is? It's similar, but not the same as that one.
3 tangent inverse of x.
It's not got 3 in it, but it has a third, which is 3, I know, but it's not 3, it's a third. What goes inside?
X divided by 3.
Yeah. So that is how you will do integrals of 1 over x squared plus 4 and 1 over x squared plus 6 or 1 over x squared plus anything. So this integral, this information is going to be used because we're going to do an integral test. And the integral test that we're going to do is 1 over n squared plus 9. Can we just assume that this guy is positive, which obviously is, and that it decreases, and just cut to the chase and find out what this fella is equal to? Now it's going to be the limit as t tends to infinity of the integral from 1 to t of 1 over x squared plus 9 dx. Now, based on what I've just told you here, isn't that integral pretty much good to go? You don't use the power rule or use subs or integration by parts. Can't we just write it down as an integral because we know that ones that look like that give you this? So we are now going to go the limit as t tends to infinity of 1/3 the inverse tan of x over 3 evaluated at 1 and at t. Are you happy about there to there without too much work? But that means you've got to memorize these kind of things or have them written down somewhere where you could, get to them easily. Now I'm ready to put in the boundaries. So it's going to be 1/3 the inverse tan of t over 3, take away 1/3 the inverse tan of 1/3. And I'm going to make no attempt to do anything with that. That's just some ugly number. This is the guy that's going to decide convergence or divergence, isn't it? This guy here. So I'm going to do brute force. Isn't infinity over 3 still infinite? Now, be really, really careful here, because there's a lot of temptation to think that this is infinite, because most things tend to be infinite, right? Square root of infinity is infinity, infinity cubed is infinity, things like that. But the inverse tan of infinity is in fact a number. if you sketch the inverse tan function, it looks like that. It actually has a horizontal tangent line. It levels off at something. What number is the inverse tan of infinity?
Pi divided by 2.
Great, so it's 1/3 pi upon 2. Take away 1/3 the inverse tan of 1/3. I guess I could make that a little bit pretty, but I'm not doing too much. Would you agree that this integral is a finite number, right? It's a number. And because it is a number, doesn't this mean that this series converges? Do I care what that number is? Not really, because in the integral test, doesn't that just tell you it converges? It doesn't tell you that this adds up to that. I mentioned that yesterday. It just says if the integral is a finite, a number, then the series converges. If the integral is infinite, it diverges. Are we okay with that question now? We're good? Right. I put that one in because I just realized that that was a situation that I hadn't looked at before. Here is another one that we are still on. This one is like 15. N equals 1 to infinity. I'm not going to do all of this one, but I am going to tell you how to do the integral. This guy is going to be the limit as t tends to infinity of 1 to t of that guy. You need some brownie points here. You deserve them if you can tell me. This is either going to be integration by parts or a u-sub. Which do you think it is going to be? Integration, u-sub. Would you agree that integration by parts really doesn't have a fighting chance? You can sometimes look at them and say, I don't care what I pick for F and G, that darn thing isn't going to get any nicer. So kind of by process of elimination, you know it's going to be u-subs. So here's
Professor,
the, yes.
Is it supposed to be 16 in the power on the bottom?
Oh
or
God,
8?
yes, it's meant to be 16.
Okay.
That makes a big difference. It's still a u-sub, but I know why I wrote 8. The next answer will probably give it away. What u-sub should I use? And I'll write it over here because it's a bit of a mess. What u-sub should I be using? To make that work?
X to the 8th power.
Is that because of my x to the 8 mistake, or did you figure out that that was the one that was going to work?
Because of your mistake.
Okay, that is good to be honest. Now you might say, well, I wonder how that's going to work, because normally wouldn't the u-sub be the entire bottom? That would be one choice, but that doesn't work. Would you agree 16 gets you 15 and it doesn't play with 7? Would you agree 8 does? And then you might think, well, yeah, okay, x to the 8 works, but that isn't x to the 8. Well, let's just take it a little bit further and show you how it does work. If you differentiate it, you get 8x to the 7. If you do the crossover, you get 8x to the 7 dx. And I do the isolate the dx one, which I kind of get quite out last time because it happened quicker than I thought. We get that. So we're going to have the limit as t tends to infinity. Don't put the boundary in. And x to the 7, this guy that I'm not going to talk about for a minute, 1 over x to the 7 du. Right, x to the 16 plus 1 has to be written in terms of u. Isn't x to the 16 just u squared. Right, x to the 8 squared. So what you get is u squared plus 1. Which means that this fella, after a little bit of cancelling, gets you 1/8 of that guy. You see it comes out quite nice as an inverse tan of u, and then turn the thing back into x to the 8 and then brute force it, and it ends up conversion. So yeah, you're going to use u subs in integration by parts, but aren't you going to sometimes have to think quite hard about the u sub? It's not going to be right, oh, it's pretty obvious it's that guy. And so that would be a good example of that question. Anything you want to ask before we move on to look at when a series converges, what does it converge to, how we can calculate that? So that's going to be the last thing. Are we good on these guys? Well, okay. Ooh, what's that? Chloe, stop bugging your brother. Right, so suppose we have that guy. And I'm picking a nice, easy fella to work with, 1 over n squared. Is that a p-series? And it is, I agree. And would you agree the p-values too? Agreed. And since that is greater than 1, doesn't it converge? So proving that it converges was pretty quick, right? A minute, done. What I want to know is, what is it, since it converges, right, it adds up to something. I would like to know what it adds up to. I'll tell you what it's not. It's not whatever the 1 to infinity of 1 over x squared dx is. Remember we told you that that's basically a curve, but we are working with rectangles, right? And so the rectangles don't add up to the area under the curve. So that's not going to be how we're going to do it. The best we can do is estimate it. Unless, as you'll find out, not in this class, but in future classes, unless there are other techniques that you'll discover that will get that as an exact value. We're just going to treat it as, let's get an estimate of this thing. Okay, if you wanted to estimate this guy, what could you do?
You could do the partial sums and then make it go to like a decently big number.
Right. And since I don't want to do you're bang on, Kira. I don't want to do a decently big number because that would take me forever in a day. But I would probably give it to some computer programmer, and couldn't they do it for me, right? They could write a little program and add up the first billion terms. And that would be really a very accurate estimate. So we're going to do a kind of baby estimate, and we're going to do what you said, but since I'm lazy, I'm only going to do S4. So what would that be? It'd be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. And that's not going to be, I totally agree, that's not going to be a very good estimate, right? Very accurate estimate, but it's going to be an estimate. And the answer I get is 1.424, right? And that's my estimate. And just like Kira said, couldn't I find S4000? And wouldn't S4000 be a better estimate? And couldn't I do S of 4 trillion? And that would be so darn close to the right answer it wouldn't matter. Because one of the things that we have discovered about series that converges is, aren't most of their values contained early on? Like the first 10 or 20 terms have most of the answer. Isn't everything else after that quite small? For instance, if I went to, let's say, the 100th term, wouldn't that guy at the end be 1/10,000th? Wouldn't that be 0.0001? Can you see that by the time you get to even, say, 100, the terms are pretty small? So the good news is that this strategy of using partial sums is very good at getting you really accurate estimates. The more terms, the more accurate. Are we good? And there is, you can go looking for it, there is a way to get your TI-84 to actually add up all the terms in a series, right? Wouldn't it be nice to have an error band? In other words, I know that my estimate is that the real answer is 1.24, but wouldn't it be nice to have plus or minus some error band? So I could say that the answer was 1.424 plus or minus 0.3. Wouldn't that be at least helpful in giving me an idea of where the answer is? So far, so good. Now, this thing called the error band has a name. It's called R, in this case, 4. R for remainder. What's left over would be another way of phrasing that when you use 4 terms. So if I can get a guy, R4, that represents this remainder, wouldn't that at least be able to take this fella and say plus or minus whatever it is? And that would give me a good idea. Pretend that we did it. If I told you the answer was plus or minus 0.3, wouldn't you at least know that the right answer was somewhere in the region from there to there, right? If I told you that it was 1.24 plus or minus 0.01, wouldn't you know that the answer was somewhere in the region that way? Wouldn't that be a much better answer, accuracy-wise, than this, right? So if we can find this guy, won't that give me an idea of how good 1.424 is, right? It could be absolutely horrible. Couldn't it be plus or minus 0.9? Which means you didn't really tell me a lot there at all. So what is the formula for R4? It's the integral from 4 to infinity of this guy. So we do use the integral not to tell us what the thing adds up to, but the integral will tell us what the error is like. And it'll tell us the error is this number or less. So this is like the worst case scenario, right? It's definitely going to be this number or less. So if we take this integral, it's going to be that guy. And that is going to have to be done using the limit as t tends to infinity again because of this fella. And this is now going to be the limit as t tends to infinity of add 1 to the power and divide by the new power. I would rewrite that before I do anything in relation to the brute force method into this. And that would be -1 over, oops, forgot my limit. It'd be the limit as t tends to infinity of -1 over t take away -1/4, so that's plus 1/4. Now, when you do brute force, you get the answer 1/4, which I would call 0.25. So my estimate for what this guy looks like, right, that fella there, was S4 plus or minus R4. And S4 ended up being 1.424, give or take 1/4. And that, I could leave it like that. Don't engineers call that? I think that's called the tolerance, isn't it? When you're an engineer, right? This is the right answer, but I could be out a little bit here on that one. Now, there is a kind of refinement on this. I know that 1/n² is definitely going to be less than that number. And the refinement is that if you go on the other side, try to find it down. And on the other side, it's R5. So rather than saying plus or minus, we can actually do the plus side is this guy and the minus side is that guy. So it's not quite symmetric. This number will be a little bit different than on this side. But that's just a refinement of it. You know how you do R5, right? You plug this guy in and you get a 5, in which case the answer is a 5th. So if I was going to do this one, it would be S4 minus a 5th. And the real answer is sandwiched somewhere between those two guys. So if you took this number and subtracted 1, the answer is bigger than that. If you took this answer and added a 1/4, the right answer is between that. So in my case, it would be 1.424 take away 0.2. And on the other side, it would be this guy, which is 1.424, add a 1/4. So on this side, it's 1.242. And on this side, it's 1.654. So I know that this answer converges, and I know it's somewhere between 1.6 and 1.2 and 1.7 roughly. That's helpful, isn't it? Now, how could I make the estimate better? There's only one thing I can do to make the estimate of this more accurate. And what would that be? It's a pretty obvious idea. What could I do to make this more accurate? Then I use only 4 terms, S4. If I wanted it to be more accurate, what would I do?
Add more terms.
Yeah, couldn't I do S400? And because the way this question works out, I can even tell you what S of 400 would look like. Wouldn't you be taking away that much on one side? And wouldn't you be adding that much on the other side? Can you see that?